So why don't we get started? Let me welcome everybody. Delighted to see you here. Once again, we have a huge turnout, and I'm sure by the time the evening's over and combining with the people on YouTube, we'll end up with more people at a virtual meeting than we would get at a real meeting. I'm really excited to have Laura Kerber here. I've heard a lot about her for a long time and delighted to have her. And I have, for the first time in a while, something to share with you all. So let's see if I can find it. Screen, advanced. All right, let's back up. I have to open this first. Okay. Here we go. Here we go. All right, folks. So this is called Throwing Stones. Come on, you got it. And basically it's about our friend Perseus. And why is he throwing stones at us? Perseus, you see him here in the classic Botticelli statue or sculpture, is holding the head of Medusa the Gorgon, he's rudely separated her head from the rest of her body. Medusa, you may remember, anybody who looked at her turned to stone. Perseus was the son of Zeus and Danae. He was a half god by birth, obviously, because Zeus is a god and Danae was just a good-looking nymph. He's the grandfather of Hercules, believe it or not. I didn't realize there was that lineage. You know, that was so long ago, it's hard to tell who's which generation, except that I know the Titans are older than the Olympians. Danae's father, Acrisius, had heard a prediction that he would be killed by his grandson. So he locks Danae in a bronze trunk to prevent her from ever being found or discovered or anything. Of course, Zeus can get through bronze trunks, just in case you didn't know that. So he manages to get Danae pregnant. And when Acrisius finds out that she's pregnant, notwithstanding what all the steps he took, he throws her into the sea. The chest lands on the island of Seraph, which is ruled by Polydectes. A young man named Dictys finds the chest, releases Danae and Perseus grows up in Dictys's house. Polydectes falls in love with Danae, but realizes the only way he's going to get to her is if she can get rid of her son. So he sends Perseus on a series of missions where he's, doing things like trying to slay the Gorgon. And of course, the plan is that Perseus will get killed doing any one of these stupid things. And then Polydectes will be able to go after Danae. But it's really not good to bet against Greek heroes. What happened, Lou would probably verify this, but basically Perseus slays the Gorgon, and on his way back, he's got this head that can turn people to stone, and unwittingly he kills Polydectes. When he hears Polydectes has been hitting on his mom, so he kills Polydectes, kills a few other people, and then accidentally actually kills Acrisius. So the prophecy comes true. He kills his grandfather. One of the things he does is free Andromeda, who is being pursued by a sea monster whom Perseus also slays. Andromeda is the daughter of Cassiopeia. And here we see them in the sky together forever. Cassiopeia, a mom, a daughter, Andromeda is there, and Perseus is still up there. And the way he's drawn by some, he's still holding the head of the Gorgon up there. This is what it looks like in your sky, looking north. I think that's northeast. No, that doesn't make any sense. There's northeast. Yeah. There's Cassiopeia. There's Andromeda. There's the M31, the Andromeda Galaxy, and here's Perseus down here. Perseus is just rising later in the night these days. So the Perseid meteor shower has already started. and it will persist until August 24th. It's from the path of Swift-Tuttle, which has a very eccentric orbit and a 133-year period. It goes from outside Pluto and all the way in. It will be back in 21, 26. So if you hang in there, that'll probably be a spectacular meteor shower in 2020, 21, 26. This meteor shower will be, the peak is going to be Monday, Tuesday, Wednesday night. And the best is going to be Tuesday morning. And I think the moon sets or rises around 1:30. So the really good time is going to be between like midnight and 1:30. Just to help you again with where it is, this is from Sky and Telescope just today. Here's the radiant. Here's Cassiopeia, Andromeda, and Perseus is right there. And that's his arm holding up the head of the Gorgon. And there's the radiant. And I just thought that just came into my mind, which is that answering the question, throwing stones, if you live with your mother-in-law forever, and there's Perseus and there's Cassiopeia and there's Andromeda, stuff's going to get thrown at you once in a while. And that's just, you know, life in the big city or life in the sky as it goes. So enjoy the Perseids next week. Hopefully the clouds will part and we'll get a couple hours of good viewing. So we're going to talk a little bit about our outreach. We have been busy, notwithstanding the pandemic. Janet called these slides pandemic outreach events. I don't know why anybody would want to do pandemic outreach, but we're doing astronomy outreach during a pandemic. I was going to rename that, but let me unmute Janet. And actually, since I'm sharing my screen, can you unmute Janet for me, Jeremy? And,
I think I did it already.
Oh, good. Why don't you take on these slides?
Okay. All right. Hi, everybody. I'm Jan Rush. I'm the outreach chair. And we did manage to do an outreach event last month. So we went to Hebner Park in Worcester Township, which is actually where the tornado was touched down a couple of days ago. But we were there pre-tornado. And we had an event that was limited to 40 people. So we did register people. So it was different than the usual star party because we were very careful about the number of people that attended. We told them they'd have to wear a mask and that they had to bring their own lawn chairs and binoculars. And we had no telescopes because we didn't want to have any issues with sharing eyepieces. So people were quite distanced and we think it worked pretty well. You can see there, Al had a station that was, he put a poster up on his car and talked about the moon, the craters on the moon, the Apollo landing sites. And we like that idea because during twilight, after people arrive, you're waiting for it to get dark. You really need something for people to do. And so for the next event, which is on the 23rd, we're going to add a couple of more stations like that to do things until it gets dark. And then after it got dark, Andrew did a tour of the planets, double stars, constellations, using a laser pointer, bringing in some mythology. And then we pointed out, Gary pointed out with his laser, the comet. And so a lot of people were able to see the comet with their binoculars. And I wanted to say also thanks to the other people who came out to work on this event with us. That was Gary and Tracy Trepisano and Mike Tucker, as well as Al and Andrew. So anyway, we think it worked. The process worked pretty well. We felt safe, and I think our attendees felt safe, and we're going to try it again on the 23rd. There we are setting up on there people are setting up on the field. You see one of the family groups setting up their little camp. And everybody followed the rules and they did fine. Then one other thing we did was in the past, we've participated in the Great American Campout, both at Temple Ambler and at Radnor. And this year, both groups went to a virtual event. So they asked us to help them with material. So we put together a series of video links and a little presentation about what to do to look at the sky while you're camping. And you can check it out at the link that's shown at the bottom there. And it's a good collection of beginner astronomy videos on YouTube, mostly without ads. So it's not a bad little collection that we might want to use for another purpose sometime. And the last thing we wanted to say is that, remember we were going to do an auction of equipment in April when it was canceled. And Jeremy has been patiently waiting to get the dog out of his living room. So we thought we would try to do an online version of that. And we're still talking about exactly how we'll accomplish it. But the reason I'm mentioning it now is that we'd really like you to, since it's been 6 months since you've thought about this, check through your closets and see if there's anything that you'd like to donate to the auction. And doing that is really simple. All you need to do is take a picture of it, send it to me, and write a little blurb about the object. It could be, 1 sentence. Make sure to mention the manufacturer and the condition if you want to. And we'll be figuring out how to get those, open up the auction to everybody that might be interested. And so stay tuned.
All right. Thanks, Janet. So let's see. I'm trying to visualize us in the Radnor Township building. Brian, you're up.
Okay, we have 2 new members this month, Michael Di Mario and Douglas Lentz. And I don't think they're here tonight, but let me just
Nope, I don't see him.
I don't see him either, but welcome. And it's funny, we seem to keep gathering about 2 to 3 members each month, even though, during the pandemic. So that's a good thing.
Yep, definitely. Great. Thanks, Brian. Lewis.
Sure.
Where'd you go?
Hello.
Lewis.
Yeah, no, I unmuted myself and then you hit
sorry.
unmute and then it muted me.
Okay.
So I was very serious. I look forward every month to this meeting, and I know we're stuck in our own homes when we'd much rather be together if that was possible. So it's really great. I reached out to all of you last month about getting an update about names and info and other stuff, and we had a really great response. About 30 people reached back to me and said either they were good or gave me corrections. So I think that's going to be good, and we're going to be reaching out to the Astronomical League with an update for them based upon that data. So thank you very much. And other than that, there's a bunch of stuff in my garage and basement and stuff that I want to auction off. These are not my stuff, they're DVAA stuff, which we want to do. So hopefully we will do well. And it's, some of them are really great scopes. They're just, they haven't received the proper love they deserve. So thank you.
Thanks, Lewis. And Lou, our newest cabinet member, astrophotography, you've been really busy. Care to tell us what's going on? Unmute yourself first. There you go.
So we've had 3 astrophotography workshops so far, and I'm going to think the next one we're going to try to schedule for next week. But we had pretty good response. What we're working on now is, this was Gary's idea actually. One particular piece of software that I'm relatively familiar with is PixInsight. It's available for free for a 45-day trial period. So the full version. So a few people downloaded that, and we're doing workshops specifically outlining some features on that to see if people feel comfortable after the 45 days to put out the $250 that it costs to buy it or something like that. It's available. It's sold in Europe, so we have it in euros. So I really don't know what the current price is, but somewhere around 250. So I'm thinking on Monday or Tuesday, we're going to do a tutorial on how to deal with noise in data in the linear state. And I'm only going to cover that one subject. So if anybody's interested, one way to be sure of what's going on, just look on the calendar on a regular basis. I usually update it once or twice a week. The other way to find out what's happening is sign on to the forum. If anybody wants to know anything about astrophotography, sign on to the forum. If you have a question, post it in the forum. You know, I'll get emailed, and you can get your answer immediately. So.
And when Lou talks about the forum, he's talking about the forum on the website, on the
That's right.
DVAA website through Club Express.
You know what?
Not the listserv.
You know what?
And you're making good use of that.
You know what, Harold? Can we go through how to sign up on that? Can you walk us through it? No, if you can.
I can do that.
It's relatively simple, and I think there was something.
Lou's going to share a screen and show us. Go ahead, Lou.
There we go. There we go.
So Lou's already signed in. Louis has already signed in.
Yeah, you have to be signed in.
Right. And then you go up to
all the way on the right.
Forums. Okay. Excellent.
All you got to do is click on there. You can go in there and change your settings so that when there's a message posted, you can get notified when there's a new message. So you can know if there's news, you can go there and look. I try to post everything on here, links to all the workshops, and any questions somebody else might have.
Does anyone know if the forums support the Tapatalk platform? And a hush falls over the crowd. Okay, I guess I'll have to try and find that out.
All right,
that's a soft application that can do multiple forums.
So if you're interested in the next workshop, which will be noise reduction, I'm probably going to have it on Monday or Tuesday. Just look at the calendar and register for the event.
Fabulous. Thank you. Thanks, Lou. You really got up to speed quickly on that. Louis, you want to liberate us?
I'm sorry. I thought I was unmuted for a second. I just want to say.
Oh yeah, go.
Yeah, I just want to say one more thing about the forum, and that is that you can go to my forum preferences, and Lou was saying how you could do things like do notifications, message delivery, send forum messages to my email, and so forth like that. So that's where you can be set up. So I'm going to liberate you now.
Thank you. All right. Nate, did you have anything you wanted to say about subsequent camping trips? Nope, I see your lips moving, but you're still muted.
I don't know if we have anything scheduled, but because we don't right now, mainly because of the virus. Yeah. But if Frank is out there, I was thinking maybe we could do something small over at his place. So Frank, if you're out there, shoot me an email and let me know what you think. Sure. But I understand that even though I couldn't go up there this year, Cherry Springs went pretty well. So I'm glad to hear that. So thanks.
Yeah, Roy wrote a great report about Cherry Springs.
Yeah, he did.
It's in the newsletter, and thank you, Roy, for writing that up.
Thank you. Yeah.
All right. Next comes Andrew with our observing report.
All right. Let me share my screen. My name is Andrew Hishner, the observing chair for DVAA, and this is the observing report for August. And while I was at the outreach event that we had going over the constellations, I wanted to make sure that, you know, I'm pointing out things like the Big Dipper and the Summer Triangle and things, and wanted to make it clear, like, hey, like these aren't actually constellations, these are asterisms. So I thought, you know, it's not something that we talk about a lot, but they're actually really cool. They're just these kind of shapes that we make of the stars, and it's kind of an artistic thing. Some of them you need to have a creative mind with, but there's a lot up there. You can see them all the way from the naked eye to the telescope. So I wanted to make sure that you know, people are aware of them, and I wanted to make a talk about it. So here's the Big Dipper, one of the most recognizable asterisms, I would say, out there. So I'll first touch base on what asterisms are, then talk about constellation-based asterisms, binocular asterisms, and also telescope asterisms. So asterisms, the formal definition is a popularly known pattern or group of stars. And again, these are not an actual constellation. So they're not officially recognized by the Astronomical Union. All 88 constellations are, and they all have boundaries. You can think of them like states almost, where certain objects are within the boundaries of a certain constellation. So that's why you might be observing something and you say, oh, that's really far from that constellation. Well, it's still technically within those constellation boundaries, which is why we associate it with that constellation. But asterisms don't have these. So you can really think of asterisms as another type of object. We usually don't think of them like that. You know, they're not an open cluster or nebula, planetary nebula, and there's no real like catalog of asterisms. They're kind of all scattered around, but they can really just be thought of just another type of object in the night sky. They can be part of a constellation. They can be within a cluster or a cluster itself, or it can just be a coincidental grouping of stars out there. So they come in a lot of different shapes and sizes. So I'll first talk about constellation-based asterisms. Now, these are asterisms that are made up of several constellations, or these can be asterisms within a constellation itself, using the stars of the constellation. And then these are all going to be really big naked eye objects that you can see. And I mentioned one of them already, so the Summer Triangle. I call it the pizza slice too. Sometimes I get a little hungry out there. So they have Deneb down here, then Vega in Lyra, and then Altair in Aquila over here. And Deneb is actually also part of another asterism called the Northern Cross. So Cygnus, the whole constellation, the wings of the swan protrude about here, but if you stop at these stars, you can make the Northern Cross, the analogous of the Southern Cross or Crux in the Southern Hemisphere. Now we have the Summer Triangle, a very prominent asterism in the summer sky. That's how you know it's going to get warm out. We're going to see a lot of galaxies. And on the other side, we have the Winter Hexagon. So a little more stars involved. And of course, we have 7 stars in the Winter Hexagon. We have Sirius, the brightest star in the sky, Procyon, Pollux and Castor, Capella, Aldebaran, and Rigel. Now, an easy way to remember which one's Castor and which one's Pollux in the twins is to remember you go Procyon, Pollux, P and P, and then Castor and Capella, C and C. So that's how I usually remember, hey, is that Castor or Pollux? You can remember by the color, or I like to remember by that little trick there. So the Winter Hexagon, you can't see it right now, but it's also a very prominent asterism. So some other asterisms, we have the sickle in Leo Major. I like to think of it as a backwards question mark here, but it's technically named the sickle. We have the teapot, Sagittarius, with the steam rising up, being the Milky Way in the sky, and then the fishhook, which is the bottom of Scorpius. And you know you have a nice horizon when you can see the very bottom of this fishhook from our latitude. Over here, we have the ice cream cone in Brody's, or you can think of it as a kite. Again, I get a little hungry out there. I think of it as an ice cream cone, goes nicely with the pizza. We have Orion's belt, these 3 stars. Again, asterisms, all different shapes. It's just 3 stars, but we associate it in our minds with this picture of a hunter, and that is his belt. And then we have the sword also down here with the Great Orion Nebula. And then Cassiopeia, the big W in the sky as well. So those are all asterisms based on constellations. We don't have, or this isn't a complete list. There are lots out there, but these are just one of the ones that I wanted to pick out. So next I'm going to talk about binocular asterisms. Now, binocular or telescope, it's hard to draw the line because of course you can get really big binoculars and then there are very small telescopes. But asterisms, technically, they're usually in the larger scale of objects. So this is just how I chose to separate things. But if you have a pair of binoculars, try the ones that I say in the telescope section. And if you have telescopes, try the ones in this binocular section. But just know that you'll usually need a wide field of view and a lower power to see the whole thing. So I first wanted to point out, another really famous asterism, the coat hanger in Vulpecula. It's technically called Collinder 399. Collinder is a catalog of open clusters. And it's just this really nice array of blue and yellow stars. It's an upside down coat hanger in the sky. Next is Kemble's Cascade. So Kemble was an observer and he actually pointed out a few asterisms. He's probably the closest to coming up with an actual asterism catalog. There are a few named after him. This is in our favorite circumpolar constellation that we very rarely go to as astronomers, Camelopardalis. And I practiced that one. Harold set the bar really high pronouncing all of those Greek god names. So I really wanted to get that one. I think I got it. So the Cascade is this really nice long trail of stars here. If you have a binocular that with a smaller field of view, you might need to go down here, and you can think of it as a waterfall leading you down to NGC 1502, down here, kind of the end of the waterfall. So it's a nice one. I like that. And then again, we have Kemble's Kite. This is in Cassiopeia. Here's the string here, and then we have the kite itself up here, followed by the string. So those are a few. Oh, here's another one. I forgot. The golf putter in Cassiopeia and a ball. So here's kind of like the Cascade. It's a line of stars. And then the putters comes out over here. And you can think of the ball, which is NGC 752. It's a pretty big ball. You might need a bigger putter for that guy. But maybe it's just these stars down here. So you need to use your imagination sometimes. But it's a nice grouping of stars. And Lambda. So Lambda Orion, which is this star right here, actually is a group of stars that make out the Greek letter lambda. So I see it, there's a few ways that you can see this. I looked at this for a while. I see it as kind of down here, and then like a line over here. Maybe it would be better rotated where this is the top and then the line comes down over here. But you can see a lambda, and you won't forget the name of this star because it's a lambda and the stars around it create a lambda. So it's kind of a coincidence. And all right, so moving on to telescope asterisms. Again, if you're going to look at these, you'll usually need a wider field of view, lower power to see the whole thing. So starting off with the 37 cluster is an NGC 2169 in Orion. So you can see the 3 here, and then the 7 over here. And this is in the Open Clusters program for the Astronomical League. It's actually very nice. I usually take a look at it if Orion's up. It's a pretty nice grouping of stars. Now we have Mini Cassiopeia in Draco. You can see the W here, and it's pretty close. Usually first thing I notice, this star would probably be down here more if it was actually Cassiopeia. But you can definitely see the W in there, and this was also observed by Kemble as well. And we have the Sailboat. This one's going to need a bit of imagination. I can kind of see it. You got the boat here, and then the sail going up over here. This is in Cassiopeia as well. So if you're interested in asterisms, again, there's a lot more than what I mentioned. You can do the Asterism Observing Program, which is part of the Astronomical League, and it's pretty simple. Just observe and sketch 100 asterisms. And with most Astronomical League programs, except for the actual sketching one. You know, the sketch, do your best. We're astronomers, not artists, although some of you are both. You need to do 5 of these 100 to be naked eye, although there's, you know, I spent 3 slides on naked eye asterisms. There's a lot out there. This will be very easy to do. And no go-to telescopes. There are some telescope-specific asterisms on the list that you'll have to do. Most of them, though, this won't be a problem because you can do naked eye and or binoculars. So it's a fun one to do. It's also a nice one to do when you just want to go out there and observe. You don't want to wait for a new moon because most of them are pretty big and pretty prominent in the sky. And that's all I got for this one. Thank you.
Thanks, Andrew. And unsure, there we go.
There we go.
Thank you very much, Andrew. I appreciate it. And my only concern is that you omitted Homer Simpson's underpants, which I know is Jeremy's favorite asterism.
That one wasn't on the list for astronomy,
So.
but you know, you can email them, so you can make a petition.
Well, we now come to the feature part of our program, and I'm very excited to have Laura here, as I've said, and I'm gonna hand the meeting over to Jeremy to introduce our guest. I would appreciate if everyone would mute themselves so that we've got maximum throughput, and we'll handle questions and stuff like that afterwards. Jeremy?
All right, thanks a lot, Harold. And for those of you who are wondering, Homer Simpson's underwear is also known as Capricornus, and will be visible in the fall. Once you see it, you can see it. All right. So tonight's presentation is going to be a really interesting one. We're very happy to have Dr. Rover with us. She's a research scientist at Kemble, which are not close here. So are taking advantage of virtual meetings and getting some speakers from outside of our local area. So Laura did her PhD in geological sciences at Brown University and also has master's degrees in engineering and geological sciences. So she has diverse research interests, including volcanology, wind or complex surfaces, the Martian climate, planetary atmospheres, and extraterrestrial cave environments, primarily with Mercury, Mars, and the Moon. As far as Odyssey, which has been in orbit around Mars since 2001. She's also the PI for the proposed moon diver mission, which will send an extreme terrain rover to the moon. Are people problem with my audio? I'm not sure what's going on here.
Yeah, I'm getting real bad audio.
All right. Yeah, for some reason my speaker's not working, so maybe my mic is out too. Anyway, tonight's presentation will be Dynamic Mars, it's to know the planet next door. So please join me and welcome Laura.
Laura, you're on.
Okay, I'm going to share my screen. Okay, I think you can see that. So yeah, if you didn't hear some of what he said, I work at the Jet Propulsion Laboratory in Los Angeles, and I'm the deputy project scientist of Mars Odyssey, which has been in orbit around Mars since 2001. And my recent adventure is that I was the principal investigator for a mission concept that's called Moondiver that we proposed to the NASA Discovery Program. And so we wanted to send Moondiver to the moon to explore lava tubes on the moon. We found some holes on the moon that are, more than 400 feet deep, and we had a rappelling rover that we're going to send down into this hole to examine the sides of the hole. And so I study volcanoes, I study wind, I study extraterrestrial cave environments, and my main thing that I study has been Mars, but I also do some work on the moon and Mercury. So today I'm going to talk to you about Mars. I really wanted to talk to you about Mars today because, recently, just a few days ago, we sent up our most recent rover to Mars, the Perseverance rover, and that's going to arrive on Mars in February. And so we're super excited about that, and everyone was staying up actually in LA, they had an earthquake just a little bit before the launch. And so people were woken up by the earthquake, and then, you know, a minute later their alarms went off. So I think the earth wanted us to know that the launch was happening so we wouldn't miss it. So these two images I have on here playing right now, the top one, there's a dust storm on Mars that was taken from orbit. You can see the dust kind of moving across the planet. And then the one on the bottom is a bunch of dust devils. Actually, I believe that's in Gale Crater. And this was kind of interesting because we had dust devils at many of our other roving landing sites, but when we got to Gale Crater, we didn't see any dust devils at first, and we thought, oh, that's so weird. We can feel the dust devils coming over with our pressure sensor, but we can't see any of them. As it turned out, we were just looking the wrong way. If you looked up Mount Sharp towards the top of the mountain, you wouldn't see any dust devils. And if you looked down towards the plain, there were a ton of them. So that was interesting. Here's a picture of me. That's at Johnson Space Center. You know, I say I live in Pasadena, I work on Mars. Normally the commute is pretty long to get all the way to Mars, but now that we're all working at home, I can do all my work at teleworking, just like everyone else. And I say, you know, I'm a geologist, so the eternal struggle of a geologist is that the history of the Earth is like a lab book that somebody's written, but then torn most of the pages out of it. So you're always struggling to figure out what is in the pages that you're missing. And so the cool thing about planetary geology is that each planet preserves some part of solar system history that might not exist on other planets. So in the case of Mars, we have a lot of history in the very earliest part of the solar system that's completely obliterated on the Earth, and we don't have a chance to study. So I know some of you know Mars probably pretty well, and then other people don't know Mars as well. I'm going to point out some facts and features about Mars, and then I'm going to, you know, kind of go into depth on some things, and you can ask me whatever questions you want. So this is the surface of Mars. This is an altitude map, and just some major things to point out. One is the hemispheric dichotomy. So Mars has a really strong lowlands in the northern hemisphere, and then it has really big highlands in the southern hemisphere. And still nobody has any idea why this is. Some of the theories are that you had a bunch of impacts that hit the northern hemisphere of Mars, and it just happens that they're all kind of in the same place. And so that's how you get that big thing. But you know, there's other planets with hemispheric dichotomies. The moon has a hemispheric dichotomy, for example, the near side, far side dichotomy. Almost everything in the solar system, somebody will blame on a giant impact. So, oh, Mercury has a large core, must be a giant impact. Venus revolves backwards, must be a giant impact. You know, the moon was formed, must be a giant impact. So it was probably a giant impact. Here's Olympus Mons, of course, the largest volcano in the solar system, and it's about the size of Arizona. That's pretty big. So it's, you know, it looks like a really big volcano, and it's really, really tall. It pretty much sticks out into space, but the actual slopes is only 1 to 2 degrees. So if you're actually standing on it, you probably wouldn't realize you were on the side of a mountain anyway. Here is Valles Marineris, the largest canyon system in the solar system. Here's how big it is compared to the United States. It's a really large canyon. And then here's the Hellas Basin, which was probably used to be an enormous inland sea. And it's one of the largest well-preserved impact basins in the solar system. So here's some of the places that we've landed on Mars. I put all of the places that we've landed as stars. And then let's see, so we have the Viking landers back in the 1970s, and then most of these things have happened since the year 2000. Pathfinder was in the late 90s. And then if you're a fan of science fiction, I also put From the Martian, the Ares 3 landing site where Mark Watney landed. That's right up there near Pathfinder. And then Red Mars, the Red Mars, Green Mars, Blue Mars series, there's their little place where they're always hanging out is called Underhill, and I pointed that out with the arrow there. And I got this from the internet. This is was an interesting thing that this guy Kyle Hill made, and he plotted out the path of Mark Watney. So spoiler alert, if you haven't watched it or read the book yet, then look away now. But so Mark Watney would have landed here at the Ares 3 landing site, and then Pathfinder is over here. And then Marth Vallis is, it's funny to read this book and to watch the movie because it's like I live here and somebody made a movie about my hometown all of a sudden because, oh yeah, I talk about Marth Vallis all the time. I'm like constantly looking at it. And some, you know, there's like a movie that actually takes place in the area you're talking about. So then the Ares 4 lander would have been here in Schiaparelli crater. And then, so here's some examples of the landing sites, that places we've landed. And you might look at them and say, wow, okay, Mars looks like pretty much a flat plane with a bunch of rocks on it. And I wanted to talk about that because here's the Viking lander, that's Pathfinder. And then over here we have Spirit, or Opportunity, Spirit, and Phoenix. And when you think about what geologists like versus what engineers like, this kind of explains why Mars always looks like a flat plane filled with like very tiny rocks. Because say if I was going to the Earth, I'm a geologist, I want to explore, this is the kind of place I would want to go to. Like, oh, wow, look at all those rocks. This is amazing. This is a picture I took in Argentina. And the engineers would say, what are you, crazy? We're not landing there. That's insane. Here's a picture. So Harold Goldner, his son Justin Goldner, we went to Iran together, and we dragged Justin out into the middle of this crazy desert in Iran. And so, you know, this is the kind of place that I would like to go if I went to Mars. Here's a tiny picture of one of our friends out in the middle of the dunes. So, you know, if I was trying to characterize what the Earth was like, I would go to a mountain-rich region. I would go to a desert. I'd go to, this is a picture I took in Antarctica, near the McMurdo Dry Valleys. This is an ice fall. And then here, Hawaii, I would go to a tropical jungle. I would go to as many places that were as different as I possibly could go. But I think if I were an engineer, I would say, what about this lovely place? This is a picture I took in Inner Mongolia. This is the Gobi Desert. Like, hey, this is nice and flat. It's so easy to land here. Like, this is the perfect place. So if you only landed in those sorts of places, you would kind of think that the entire Earth looked like a parking lot. And the biggest, you can even tell the difference here, like for Viking, and Pathfinder, we didn't have images good enough to know how many rocks there were where we were going. And so you can see this big change when we finally got images to figure out where were the places with the least rocks possible. Then we started landing there instead of the places we had been landing, because these places we had been landing were kind of dangerous. So we've been kind of pushing the envelope and saying like, hey, can you go to places that have a bit more topography and a few more rocks to look at from the geological perspective? So just to give a little overview of Mars, here's the size of Mars compared to the Earth. The surface area of Mars is about the same as the surface area of the continents of the Earth. So I like to think, if you're thinking about exploring Mars, imagine that there is an Earth for which every continent remains unexplored. And that's the sort of landmass you're looking at on the New World. And then here's some of my favorite pictures if you're in the market for abstract art. These are sand dunes on the surface of Mars. On Earth, most sand dunes are white or tan, and they're white or tan because we have a lot of quartz. And quartz is a mineral that breaks conchoidally. It doesn't have a lot of cleavages, and so it's really tough, physically tough, and it gets tumbled around and it's fine. So the Sahara dunes in the Sahara, they're totally almost 100% made of quartz a lot of times. On Mars, we don't have a lot of quartz because quartz requires plate tectonics and things that get recycled a bunch of times. Mars is mostly made out of basalt. And so we get sand dunes that are made out of basaltic minerals, especially olivine. Olivine is a mineral that's very easy to break down with water, but it's very hard to break down physically. Physically very strong, just like quartz. And so you end up with these sand dunes that are black and sort of greenish. Here's some sort of greenish olivine-rich sand dunes. And olivine is if you know the gem peridot, it's the same, the gem version of olivine is peridot. And here's a lava flow on Mars. This is one of the very more recent lava flows. Only a couple millions of years old. Here's a picture of the South Pole layered deposits. So all of that over there is water ice with a little bit of CO2 ice on it. And then in the right-hand part of the picture, all of those black sand dunes again. Here's a cool picture. This is from the North Polar Layer deposits. And at the top, there's ice and CO2 ice. And then there's kind of some sediments below that, which is the red stuff. And our spacecraft actually captured avalanche that was happening at the time. The spacecraft just happened to capture the avalanche happening from the edge. So this is the top of the cliff, and that's the bottom of the cliff. Let's see if I can advance. Okay, yeah, so this picture you might think is quite interesting. Here's a crater on Mars in Meridiani Planum, and you see all these little lines at the top, and those are all tracks from our Opportunity rover. So every time you see a little node here, it's where Opportunity was turning around in place, and then it went all the way around the edges of this crater. One very interesting sort of non-Earth-like process that happens on Mars is these geysers that we get near the South Pole. So what happens in the winter, CO2 from the atmosphere condenses on the pole, and then it kind of builds up over the winter. And then in the spring, it starts to sublime. And what you get is very clear pieces of CO2 ice, and underneath them is black sand. And the sun shines through the ice and starts heating up the black sand. And so pressure builds up at the bottom of the ice, and then eventually breaks through the ice, and then black sand comes out and goes all over the place. And we call them, the results of them, we call spiders. And they're kind of a very beautiful, there's actually a citizen science effort that going into mapping all of these spiders all over the South Pole. And other beautiful things having to do with the CO2 spring, these are sand dunes near the North Pole, and you get the white CO2, and then you get the salmon colored dust, and then the black sand dunes. And so when the sand dunes are saltating forward, all the avalanches on their sides where they're moving towards are super black, and you get these sort of Dalmatian dunes that come every spring. And here's another, this is my favorite like abstract Mars image. Here's a bunch of those kind of Dalmatian dunes, all covered in CO2 that's slowly subliming in the springtime. Here's an interesting terrain. It's called the Swiss cheese terrain for obvious reasons. And this is all CO2 ice. And there's little imperfections that form in the CO2 ice, and they form nuclei for sublimation of CO2. And then it grows throughout the seasons. And this is actually, they call it a secular process. So this is happening year to year. This CO2 ice is going away. So it's part of a very multi-year climate change on Mars. So here's some examples throughout the years. They took different pictures of the same area, and they can see this Swiss cheese terrain is slowly growing. So where is this CO2 going? It's probably going, I mean, it goes into the atmosphere, and ultimately it'll probably end up at the other pole, at the North Pole. Here's something that I wrote a paper about recently. These are huge, they look like a spider web or something, but they're big walls of basalt. And so what we think happened was that there was a bunch of mesas, and they were all fractures, kind of big fractures going everywhere. And then lava just filled up all of the fractures. And then as it erodes, it just leaves this spider web. So the closest example we have to this on Earth is the Shiprock dike. This is out in Arizona. And so it's just like a big blade of lava rock. Except for the case on Mars, these blade-like walls are more than 50 meters tall. So I always say if there was some kind of national park system on Mars, I definitely think this one would be in it, and would be the favorite of all the rock climbers around. Here's a really far away version of the same features. So this was a very interesting thing to find. It looks like a big alligator to me. Here's another weird thing. You know, I think people think that the Mars scientists know everything about Mars history. There's a lot of stuff we have just absolutely no idea what it is. And one of those things is the taffy terrain. The taffy terrain looks kind of like if you had a lot of salt tectonics, kind of like they have on the floor of the Gulf of Mexico, for example. But you know, we never get to see the Gulf of Mexico exposed. This is at the bottom of Hellas Basin. So it used to be a giant sea, and now it's all gone. And we have this totally bizarre terrain. Really, very few people write papers about this because they just don't know what it is. So as time has gone on, our dreams have come true. Our very smart engineers have made it possible for us to land in smaller and smaller ellipses. And so this particular ellipse for the Curiosity rover in 2011, it actually landed almost, was it 8 years ago or something they were saying? So it's near a mountain. And so it's been making its way up this mountain, which is called Mount Sharp, over the past 8 years and looking at everything as it goes along. And so that's very exciting. And then, of course, as I was telling you, the Perseverance rover just launched. It's going to be landing in February, and I'll tell you a little bit later in the talk what it's going to be looking at. I wanted to tell you a little bit about what it's taking with it. It has a mass cam with a zoom lens, which we've never had before. It has a super cam, which is, you know, Curiosity has a similar thing called chem, which is a laser that shoots like a laser out at a rock and vaporizes it, and then measures the spectra of the dust that comes out, and then it figures out what the composition of the rock is. The EE cams are engineering cameras. META is a meteorology station. MOXIE is really cool. It's a in situ resource utilization, as they call it, device which makes oxygen from the CO2 in the atmosphere. And so the idea is that they wanted to test, can we make oxygen, so that in the future they can try and make oxygen for astronauts. The RIMFAX is a ground penetrating radar that's going to see layers under the surface. We have the power source on the back here, which is the nuclear power source. We have the this is for the samples. And so Mars 2020's big goal is to collect a bunch of samples in tiny little tubes. And then later we're going to retrieve those samples and bring them all the way back to the Earth. So Mars 2020 is the first step in a 3-mission long sample return campaign that we're just getting started on. Then on the arm here, we have, I'm going to try and, okay, turn the sound off. On the arm here, we have a couple instruments. We have the drill that collects the samples. We have Sherlock and Pixel, who are, those instruments were both made at JPL. So I feel very connected to them. They're both made in my building. Sherlock is a Raman spectrometer. It does composition of things. And then Pixel is actually an X-ray spectrometer. So it gets the elemental composition of the surface. And interestingly enough, when they were testing Pixel in the basement of our building, it would make this really high-pitched whistle, like this crazy, like mechanical nightingale sound out the back of the building all the time. So you could always tell when the testing was on because it would make this crazy sound. And then one day I heard the sound when I was all the way across the other side of lab. And I thought, well, this is very weird because Pixel's not anywhere near here. What is this sound? And as it turned out, it was like a grackle that had imitated the Pixel testing sound and was singing it on the other side of lab. So I thought that was interesting. Here's a picture that somebody on the internet took of the launch of Perseverance rover. They took it from the air, which was pretty cool. And the other cool thing we have on Perseverance rover is we have a little helicopter. It's like a dual rotor helicopter. It's a tiny little, well, it's not tiny. It's compared to a person, it's pretty big, but it's the first time we would ever fly a rotorcraft on another planet. And so that's pretty exciting. It's just a tech demo, so it doesn't have any particular goals except for to go up in the air, take a bunch of pictures and come back down. But we have a lot of plans for the future to like increase the amount of rotorcraft that we send to other planets. So now I'm going to tell you a little bit about the history of Mars. I call it a tragedy in 3 acts because the history of Mars, it's kind of like how a planet that seemed really nice went kind of wrong. So in the ancient days, we call it the Noachian period after Noah. It's like so old that it's Noachian, you know. And so Mars was a lovely place with rivers. And so I included this animated GIF of a meandering river on the Earth that was taken over the last 30 years or so. And so it's leaving all these meanders as it's going along. This is in the Amazon. And then here's a similar meander on Mars that got preserved all this time in the Eberswalde region. And so Mars was a nice place. It seems like it rained. It seems like there were lakes that filled up with water and then emptied out the other side. It was raining. So, you know, it was a nice place at some point. Here's another animated GIF. This is of the desert Southwest, and you can see sort of the draining of this lake. I think this is Lake Mead. And so all of the water kind of going away. So this is what we imagine happened on Mars. In this particular picture, you can see that there was water coming into this crater, forming a lake, and then filling it up so much that it could spill out the other side. So that's a way that we can figure out how much water was filling some of these lakes. And we know it had to be enough to come out the other side. So this brings us to Jezero Crater. Jezero Crater is the landing site of the Perseverance rover. And up in the corner, I have a picture of the whole Jezero Crater. It is one of these kind of lakes that has both an inlet and an outlet. And at the inlet, it has this enormous delta, which is very exciting. So we're going to land somewhere in here on this flat region. And then we're going to drive up. I think I included all of these colors, by the way, are different minerals that have been detected, like clays and other things. So here's the Jezero Delta, and the idea is to land somewhere in here and then drive up this delta. And then we had this kind of compromise because a lot of other people wanted a site to land in that was outside Jezero by a bit, you know, maybe like 50 kilometers away or so. No, I think it was 30 kilometers away. And so they got in a big fight about where they should land. And then finally the Jezero people said, hey, you know, if we landed in Jezero, we could drive midway to your site, which is called Northeast Syrtis. And then we could see both of the kinds of rock units that we're looking for. And so everyone thought that that was a splendid idea. And so that's what they're probably going to do. The other good thing about Midway is that, of course, it's going to collect all these samples. Then we have to send another mission to go grab the samples and blast off into orbit. And so we had to choose a place where this rover is going to end up in a spot where it's possible to land. And Midway was a place that was possible to land. So that everyone is super excited about that. This whole thing should, you know, take place over a number of years. And then we'll send the mission to go get it maybe in 2026 or 2028. So the thing that, you know, you think, okay, the cool thing about Jezero is that we're going to sample and bring back rocks in the time period when it was most possible for Mars to host life. And we're going to go look in a lake environment, in a delta environment, which is really a good place to preserve the signs of life. And so this is one of, you know, we've been looking for life on Mars for a long time, but we haven't really had the proper tools to properly look for life on Mars. And so now we're finally going to have the proper tools because we're going to actually take samples. The instruments we chose are really good for looking at living things like the Raman spectrometer, and we're going to bring them back to Earth where we have all the instruments on Earth to look at them. It gives us a real good chance of actually seeing whether or not there's life on Mars. But then, you know, the tragedy part of Mars is like, oh yeah, it was a really nice place, there was life and stuff. And then now it's this kind of colder polar desert. So what happened? Everyone's very curious. What makes a planet that seems quite habitable become a planet that's a desert like Mars is today? And so that's kind of what Curiosity, the previous rover, was sent to explore. It went to Gale Crater, which is about halfway around the planet from Jezero Crater. And in the middle of Gale Crater was a big mountain. And at the bottom of the mountain, we could see all these clay. It used to be a lake. There's a little delta there as well. But then as you went up the mountain, there's this huge sulfate bearing unit. And we found sulfurous rocks all over the place on Mars, and they're very highly correlated with a specific period when habitability ended. It's also pretty well correlated with the time when huge volcanic plains covered up this maybe 30% of the Martian surface. So it's probably not an accident that the end of the habitable times coincided with this enormous volcanic eruption that covered up 30% of Mars. But other things that were happening at this time was Mars was lost its magnetic field, and so it could no longer protect its atmosphere against the solar wind. So it was losing its atmosphere to the solar wind. And then as it lost its atmosphere, of course, the pressure drops and then water is no longer stable on the surface. So right now, Mars is right at the triple point of water, where it's right where it can be a liquid, a solid, and a gas all at the same time. But there's so little water around, and if there's any wind or anything, it can still evaporate. So we have almost no liquid water on the surface of Mars today. But if you raise the pressure just a little bit, you can get some more liquid water like we had in the past. So right now, actually, Curiosity has been going, oh, we're, you know, for the past so many years, we found so many interesting things in this lake part of Gale Crater that we actually are still not at the sulfate part. We're right up here on the green hue pediment, and then, you know, probably like a couple weeks or months away from finally getting to the sulfate. So I'm super excited. It's like I've been waiting for this moment the whole time that they've been on the surface. Get to the sulfates and see the transition from nice to live Mars to like some terrible acidic sulfur covered brimstone Mars. So during this time period, everything cooled off a lot. And then you stopped having river valleys. But what you did get is these huge outflow channels. They call the catastrophic outflow channels. And these come out of fissures in the ground. And it's just a catastrophic flood that comes out of fissure in the ground. So there's two theories about how these came to be. One, that you started freezing the top of the Martian surface into a cryosphere. And then the cryosphere was, pretty continuous with ice. But occasionally, if you broke through it, you would have an aquifer that's under great pressure down below where it's still a bit warmer. And then all of that water would come out like crazy. And then the other theory that I'm actually partisan to is that this isn't a water flood at all, but it's just a flood of extremely fluid lavas. And they were not part of the dying wet Mars. They're more like part of the reason why Mars was dying. So there's three periods of Martian history. There's the Noachian. That period that I was just talking about is the Hesperian. It's just named after a part of Mars, which means western area, Hesperian, after Hesperia. And then the last time is the Amazonian period. And that's actually the longest period of Martian history from about 3 billion years ago to today. And so during this period, a lot of interesting things happening, mostly glaciation. So at this point, Mars is a cold polar desert, and it has glaciers. So here's a glacier I show on Mars. This is from Antarctica. It's a rock-covered glacier. And then this is a glacier that we have on Mars. Yeah, this is Earth, this is Mars. And so we have glaciation all over the place. I just wanted to show you this video, if I can make it work. Oh. I don't know if that's working for you guys, but this is an animated GIF that shows how those glacier features get formed. They kind of, if you ever want to look at the coolest animated GIFs ever, Google Earth has a thing called Google Earth Engine, and it's basically a 30-year time lapse of the Earth's surface, but it's on the Google Earth platform, so you can zoom into anywhere you want. So you can see islands forming off the coast of Cape Cod, and you can see, desertification or cutting down the Amazon rainforest if you want to. I don't look at that stuff, but then you can see like sand dunes moving. It's fascinating. And if you go to the poles, you can see all the glaciers moving. And so what's been happening over the last 3 billion years is basically Mars moves around. It has a really strong obliquity. Right now, Mars has about the same tilt as the Earth. It's about 25 degrees, and the Earth is 23.5. And so Mars happens to be sort of close to us, but Mars is, while the Earth's axis stays pretty close to where it is now, and the movements that it does make cause ice ages and stuff, Mars just wobbles drastically. So you can see these are two graphs showing the obliquity of the Earth not changing that much, and the obliquity of Mars, which changes hugely. And the reason for this is that Earth has a moon that actually keeps it from wobbling too much. Mars doesn't have a moon, so it's kind of tugged back and forth by the orbits of the other planets, and it can go up to 60 degrees obliquity. And when that happens, all the ice that's currently at the Martian poles comes down to the equator, and then it'll go back to the poles. So you have all this weird glaciation going on. In 2015, what is Mars like today? I wanted to sort of bring us into the present of Mars. In 2015, we had a workshop where we talked about if we did move to Mars and we tried to make a base there, where would we want to settle? And so everyone put in a proposal was where they wanted to settle. And this was the place that I wanted to go. These features here are called yardangs. So in that picture that I showed of Justin Goldner in the desert, those were yardangs on the Earth. And these yardangs on Mars, they're wind eroded hills. So wind blows all the time from the same direction. It forms these aerodynamic shapes called yardangs. But these can be 100 meters tall. They're really tall features. So I said, oh, okay, what I propose is that we land at the edge of these yardangs, and then, there's still a lot of radiation risk on Mars, and you want to protect the people from the radiation. So why don't you burrow into the sides of these yardings and build your cities in there? And then you don't have to live underground, but you're still going to be protected from the radiation from most of the angles that you would worry about. And then you kind of have an endless, and this is a huge sheet of volcanic ash, you'd have an endless place where you can burrow here and there and make warrens of places to live. And, you know, as you explore it either direction, you can make caches of food and little places. And so this was my spot that I proposed. This is another picture from the Lut Desert in Iran, and this is a truck here, so you can see the size. These are the largest yardings on Earth. There's about 70 meters tall, and on Mars they can be 100 meters tall, 200 meters tall. They can be kilometers, hundreds of kilometers long. They're really enormous. And here's an example. I went to China to see some yardings, and I was delighted to find that people were already living in them. So if you imagine your little Martian home, this might be what it'd be like. Here's the people's doors inside the side of this yarding. This is all like old lake sediments they're building it in. And they actually have, you know, brooms for the dust, and they have a little satellite dish to talk to their home with. So that's a perfect analog. So imagine my yarding town, and then I photoshopped a town over it. And I took all of these imprints of Soviet rocket launch facilities, and I put it on the flat ground out here. So you could say, okay, this is where you live. It's nice and rough, lots of geology, and then you can land in a nice flat surface out where engineers like in front of it. So what would it be like to live in my yarding town on Mars? Well, the length of the Martian day is about 1 day and 40 minutes. And so it's when you're living on Mars time, when the rover first lands, most people live on Mars time, and they even have little Mars watches that people can have. So you get to sleep in 40 minutes every day, which starts out being awesome. But after a while, you get totally off of everything. And, you know, the older missions like Curiosity will run those not on Mars time. It's a little more inefficient use of our resources, but it's a lot more efficient as far as people's sanity goes. So when Mars 2020 first lands, I don't know if they plan to do any Mars time this time, but in all the past missions, they've done, you know, a couple months where everyone lives on Mars time. Then the length of the year, you know, it's about twice the Earth year. And so if you live there, then you'd have a birthday only once every 2 years. So you'd be half as old as you are now, which is nice. And you'd only weigh, you know, like about a third of what you weigh now, because the gravity of Mars is only 3.7 kilograms per second squared. And then the lighting, the sun is about 40% as bright. So it's actually not too bad. And it can be cloudy on Mars, but it's not usually that cloudy. So what would it look like in your yarding house? I think people think that space stations would be very slick and smooth with like panels that you can't even see, but that's usually not the case. I just like to show this image of my advisor's office. This is when I was getting my PhD. These are all of his globes of every single planet, and then he had flags of every country, and then he had huge monitors to look at and space symbols and patches and stuff. So I imagine the inside of that place would look a little bit more like that. Of course, the time that you'd have to wait to talk to home can vary a lot, be up to 40 minutes sometimes. And sometimes you can't even talk to home at all, because when you're in opposition and the Earth and Mars are on opposite sides of the sun, then you can't talk. Like usually if we want to take a vacation, we'll do it during this opposition period, because during conjunction rather, because we can't talk to our spacecraft anyway. So this is not happening right now. Right now, Mars and the Earth are pretty close together, and that's why everybody's launching their spacecraft right now. You only have one chance every 2 years to launch your spacecraft to Mars when it's close by. So what would the weather be like? Here's some weather curves from the Spirit rover. It's actually at Curiosity, it's gotten over 70 degrees on our thermometers. That's Fahrenheit, so like 20 something degrees Celsius. And so it's actually not that bad during the day. Sometimes, okay, it can go down to like, 0 Fahrenheit. But then it's the nighttime that really gets you. The atmosphere is really thin. It doesn't hold heat well. It doesn't have good thermal inertia. And so at night it gets down to like -100 Fahrenheit. Very cold. But in the morning, it's kind of cool. This is something we usually took a picture of Mars only at 3 o'clock in the afternoon. And then in some of our later missions and the European mission, Mars Express, it's been taking pictures of things from all different times of day. And here is a picture of some fog that was in the bottom of Valles Marineris in the morning. At the Viking 2 landing site, it was far enough north that you got frost on the rocks in the morning. And then Phoenix was a kind of a more polar lander, and lots of clouds. It had this lovely camera that took pictures of all the clouds rolling by. And these are the clouds at night rolling by over Phoenix's head. So if it's a nice day on Mars, you'll get some dust devils. These are just caused by, heating up of the surface and convection happening. So these are very common across the surface. Here's some pictures of dust devils. These, you have your normal dust devils on the Earth. Some of these dust devils on Mars can be 12 kilometers high. So they're a lot like tornadoes, but they're not very strong because the Martian atmosphere is pretty low density. And then here's some sand dunes. The sand dunes hardly ever move, but you can see them moving if you look over a long period of time, a couple years. We have some images now that are 10 years apart, and you can see these sand dunes kind of marching across the surface. And then if you're on Mars in a bad day, we'd have what we call a haboob, which is a dust storm. This is what killed our Opportunity rover a couple years ago. It was usually the tau, or the optical opacity of Mars, is about 0.5, maybe 1 is a really bad day on Mars. And the last measurement that Opportunity gave us was 11, and it's a logarithmic scale. So it was probably 99.9% of all solar energy was being blocked out at the Opportunity landing site. And Opportunity is a solar powered rover, so it was not doing real well. I included this picture from the movie Mad Max Fury Road. I feel like if you haven't seen that movie, it looks like it's about Mars, because there's a guy who's hoarding all the water. The water is stuck inside this enormous cliff, and he just lets it out whenever he wants to. That's kind of how Mars is. It's got a ton of water, but it's all ice, and it's all stuck under some rocks, or like behind something, or at the pole. And so, and then they're always going around and getting stuck in the mud, and like a giant dust storm is coming along. So I said, oh, this is Mad Max on Mars. Here's a picture from 2001 of when one of those dust storms turned into a global dust storm. And you can see it's very clear in June, and then it just becomes totally impossible to see anything by September. Here's some more pictures from Phoenix of those clouds rolling by. I feel like oftentimes when you see pictures of Mars, we intentionally we take all the images that have clouds and we take them out so you can get a good view of the geology. But there's actually a lot of clouds, especially over the top of the volcanoes or deep in that Hellas basin I told you about. It's really cloudy. And then here's a sunset on Mars. The sun would look slightly bluish on Mars, and it would be just enough smaller so that you'd feel like you're in a weird place. If you were out at night, of course, you could see most of the stars that we usually see. It was really funny because we were on this telecon and we were trying to figure out how astronauts would navigate on the surface of Mars. And then, people were saying, oh, we're going to need a fleet of GPS satellites and stuff. Like, how are they going to know where they are? And then someone said, like, well, could they just use the stars to navigate? And everyone was like, oh, yeah, I think they could. And so here you would see a beautiful sky of stars, of course, but then, it's kind of dusty in the atmosphere of Mars, so that would affect it. And then we have the two moons, Phobos and Deimos. Phobos is way smaller than our moon, but it's also way, way closer to the surface of Mars than our moon is. And so the apparent size in the sky is actually, it's maybe like a quarter of the size of our moon. And then it goes across the sky every day a bunch of times. It only takes 4 hours to go across the sky because it has an 8-hour total orbit. And so you'll see it rising in the west and setting in the east. So this is a picture. I wanted to sum up and talk a little bit about the future of Mars exploration. This is a beautiful picture of Valles Marineris that was taken by the Indian spacecraft. It was called the Mars Orbiting Mission, or MOM is what we called it. And so the Indian spacecraft was really great, came there a couple years ago and took a bunch of good pictures. And then coming up, so far, the only people that have landed on Mars successfully is the United States. There's been a lot of tries by other countries, and so far they've failed. We've had a lot of successful orbiters from other countries. We have the Indian one, we have two European satellites that are around Mars right now. One of them just got there pretty recently and it's taken amazing data. And so, but then a lot of people are coming. It's like the democratization of Mars going on, or the internationalization of Mars. So one of the big ones is the United Arab Emirates just launched a big satellite that's going to go and orbit around Mars. And this was a partnership with the University of Colorado, actually. And so the University of Colorado, that's where this was built, but in partnership with the UAE. It's called HOPE. And then the other one that just launched was the Chinese one. The Chinese, you know, have never been to Mars so far, but it's go big or go home. They sent an orbiter, they sent a lander, and then on the lander is a rover. And so that should be landing next year as well. And then Mars 2020, which I told you just launched. And then the Europeans have a rover. It's a coordinated effort with the Russians. So the Russians are building the lander and the Europeans have this rover, and it's called the ExoMars rover. It was supposed to launch also in the same time period in 2020, but it bumped to 2022. And then in 2024, there's the Japanese mission called MMX, which is a mission to the Martian moons. So it's going to be a Phobos sample return, which is very exciting. So there's tons of stuff going on Mars, and it's all very exciting. So with that, I'll leave you with my photoshopped version of some astronaut being on Mars, and I'll take any questions that you have.
Jeremy, if your audio is good, why don't you handle the questions?
All right, can you hear me?
Yep.
Yes.
All right, yeah, I don't know why everything was strange for a couple minutes there. Yeah, so any questions for Laura? This is a great talk.
Should we just talk or chat?
Yeah, you can do it either way.
You can talk.
Okay. Mike Tucker here. Very, very good talk. You talk very fast. People say I talk fast and talk even faster than I do. The pictures were absolutely incredible. The ones from the landers themselves were obvious and very good, but the ones that really got me excited were the high angle shots. From what craft were they taken?
So most of the ones I showed were taken from the Mars Reconnaissance Orbiter, and that one got there in 2006, I believe. And that one has a thing called high rise, and it takes pictures at a resolution of 30 centimeters per pixel. So you could see a dinner plate on Mars. It's amazing. It's a huge telescope. And actually there's a thing called High Wish, and you can go to a website and you can request that they take a picture of anywhere of Mars that you want, and then they'll take it. It usually takes about 6 months for them to target your spot, and then you'll get an email saying like, hey, we took your picture of Mars. And so I put them in there all the time, and then it's such a delight when I get an email back saying like, hey, they took your picture of Mars, and anyone can do it. It's super fun. Yeah, so High Wish is the name of the site, and High Rise is the camera.
Thank you.
Laura, I had a question. In a lot of science fiction, you hear about, like the Red Mars series, you read about terraforming, and in the FX series Mars, they talk about mining. As a geologist, how realistic are either of those prospects, terraforming or is there anything there to really mine?
I'll start with mining. Mining, you know, there's nothing so valuable on Mars that you would mine it to bring it back to the Earth. There are some asteroids out there that are high in platinum or other really precious metals that people would think they might be valuable enough to go and mine and then sell on the Earth. On Mars, you can mine things. There's tons of iron. There's, you know, other sorts of interesting minerals. There's probably less stuff like gold and all of that on the surface of Mars, just because how it's usually concentrated on Earth. But so you could do tons of mining, but it would probably be to support a colony that's on Mars so that you wouldn't have to import everything from the Earth. And people are working pretty hard on that. Like the number one thing people are trying to get is water, because you can make rocket fuel out of water, and then you can also drink the water, and you can make oxygen and all this kind of stuff. And so they're focused in on the polar caps and the places above 40 degrees latitude that have glaciers and stuff like that. But you could mine all sorts of other things. As far as terraforming goes, it's pretty difficult. What you would have to try and do is get the pressure of Mars to be greater. And there's some ways you can do that, like on the south pole of Mars, there's a big ice cap. And recently they discovered that usually in the winter there's CO2, and then there's a water ice cap, and then there's actually more CO2 that's hidden under there that they didn't know about. And they think if you drilled through the water ice cap and liberated that CO2 from where it's trapped underneath, you could maybe double the pressure of Mars. But you know, Mars is only 6 millibars. If you doubled it, it would be 12 millibars. You need it to be more than about 50 millibars in order for a human being to go outside without a pressure suit on. And so you still have a long way to go before, like, where are you going to get all that pressure? So some people are thinking, well, carbon is sequestered in carbonate rocks. If they found a bunch of carbonate rocks, could they bake them out and then liberate all the CO2 out of those rocks? And so eventually get it to a high enough pressure where you could go outside without a pressure suit, but you still have to wear an oxygen mask and a bunch of coats and stuff. If you wanted enough oxygen to breathe, that's even harder. On the Earth, that was done by life forms. So you'd have to have tons of like photosynthetic algae or something to do that. So one of the things me and my colleague have been promoting is that if you take like an aerogel to Mars, you can make a little greenhouse that's passive. And if you just set up a little dome of aerogel, it's very insulating. So you can make a habitable environment, but on a very small scale. So you'd be like, oh, I'm terraforming, but really local terraforming. And you wouldn't have to keep pumping like heat into the system. It would take care, that part would take care of itself, but you would have to, it would be hard to scale up to a whole planet. So anyway, it's a challenge. I think it's worth thinking about, and Red Mars actually handles the challenge really well. I think he goes into a lot of the mechanics behind it, and so it's one of those things that seems impossible now, but I wouldn't put a limit on human ingenuity.
Thanks. Hey, Laura, I have a question for you about obliquity. I was very interested when the whole thing you talked about, you know, the axis turning to almost 60 degrees. And so did that mean the poles just shifted and reformed in the same new axis of rotation, or what consequences did something like that have?
Yeah, so in this case, the rotational pole would stay the same, but it would tilt towards, it would like be like a top, and it would spin like this. And so the thing is that Mars is an oblate spheroid, so it's shaped like that. And so as you tilt it like this, then it gets tugged more by other planets, and then it gets tilted back and stuff. So it has a crazy, crazy effect on Mars's climate. But I would say that's the major effect on the climate. It doesn't have as much an effect on the rotation.
I got it. And can I ask a related question? What was like sort of the period where it would have these wild swings? Are we talking millennia, million years, trillion years? I mean, how?
It's more like tens of thousands of years.
Okay.
That would have this. You saw the diagram I showed where it's kind of like, what they did is they took the entire solar system and they calculated backwards where all the planets would be, and then they tried to figure out what the obliquity would be. And the solution to that is well known for a couple million years, and then after that there's too many variables, and so it's a chaotic solution. And so they have different solution families, and they'll show that most of the time Mars stays in a particular obliquity envelope for a while, and then it changes to a different obliquity envelope and has those little, you know, tens of thousands of years changes, and then over millions of years cycle it'll move back down to another spot. So it's an interesting problem.
Thank you.
Hi, I was wondering if there are any discussions about the design of the rovers in terms of like cosmetics.
Like whether or not they look good?
Yeah.
Yeah, so most of the time, no. Most of the time it's like it's just functional, and so they don't care how it looks. The very few times they've done anything that is like a little bit cosmetic, like on Curiosity, they had its wheels, and they put little holes in the wheels that spelled JPL in Morse code. And the reason they did that is because on some of our first spacecraft that JPL made, we put a giant JPL signature on it, and NASA said, guys, we don't want you to do that, taking pictures a million times that say JPL. We want it to be a NASA thing. And so we have big NASA insignia and American flag, but JPL is not allowed to be on there. And so the JPL engineers were like, well, we built this, like we should put something on it. And so they put this JPL in Morse code on the wheels, so that every time the rover would drive, it would like make an imprint of JPL on the surface. So, yeah, besides that, I don't think they think very much about how it looks.
Okay, thank you. I thought it could be sort of like a propaganda and even like increase the budget of NASA potentially.
If it looked good.
Yeah.
Yeah,
like a money shot.
It's actually kind of funny because SpaceX does think about that. And like Elon Musk was saying, he designed his own spacesuit, and he was saying, the spacesuits look horrible. You look like a marshmallow. Like, I want a spacesuit where my butt looks good in it. Everyone's like, wow, okay, that was never a thing. But I think he does have a point that like things that look good, and on the Curiosity rover, it had that huge eye, and everybody thought, oh, that looks like more like a creature having this huge eye, even though the eye is just for shooting like deadly lasers from. And then we had a little microscope on Curiosity that took pictures of the ground, but then they had it could focus anywhere from really close to infinity. And that was useful because then it could take a selfie. And, the engineers don't care like whether it takes a selfie, but then once it does take a selfie, everybody loves it. And they love seeing selfies from Curiosity. And so I think from now on, since it was so popular, it's probably going to be a feature that's always going to be on the rovers.
Go ahead.
Yeah. Oh, did you want to ask another question?
Yes, I did. Thank you. You mentioned about the RTG powering one of the landers. Is this one of the first ones in quite a while that had an RTG?
So Curiosity had an RTG, and that was the last one we sent. And so this new one is almost an exact copy of the old one. They just put new wheels on it and some new instruments, but they're both nuclear powered.
Okay, great. Thank you.
And the Pluto mission was also nuclear powered.
Yes.
Yeah, that was a little while.
I heard that, right.
Yeah.
I have a question. This is Isaias. That was my son asking a question about the aesthetics of the rover. He was thinking that if it looked like an Apple product, maybe there will be more support for NASA. But the question I have for you is regarding the atmosphere of Mars. Mm-hmm. So one of the things I heard is that Mars lost its atmosphere because it doesn't have a magnetic field. So, and yet another planet, which is another rocky planet, Venus, has an atmosphere. Does Venus have a magnetic field that it's holding its atmosphere? So what is the difference between the two?
Yeah, that's a great question. So Venus does not have a magnetic field. Mercury has a magnetic field and has no atmosphere. Venus has this enormous atmosphere, and yet it doesn't have a magnetic field. Then the Earth has, pretty thick atmosphere and a magnetic field. Mars, used to have a magnetic field, but no longer does. So it's some combination of Venus spins extremely slowly. That helps a lot, because if you spin faster, then you lose your atmosphere faster. Venus also has it's a thick enough atmosphere that the atmosphere starts to protect itself. Like it'll form a haze around the top of the atmosphere that stops stops particles from getting in further, and then stops the particles from breaking up. Because really what loses your atmosphere is you have photons that come in and break apart like a water molecule or something, and the hydrogen is so light that the hydrogen escapes. And so if you can stop that kind of escape from happening, then it helps. But a lot of that stuff, like we just sent a spacecraft to Mars called MAVEN, and it's supposed to be measuring how the atmosphere interacts with the atmosphere, with the solar wind. how the solar wind strips away the atmosphere that's left. And part of that question is like, why and how did Mars lose its atmosphere? And was it something that was always destined to happen, or was it, just sort of a fluke of history? And then the other half of it is your atmosphere is being stripped away by the solar wind, but then it's also being replenished by volcanoes.
Okay.
So if Mars volcanism shut down a lot sooner than the Venusian volcanism, Venus would still be pumping out atmosphere all the time. Mars would have stopped pumping out atmosphere, and then it would lose it all. So it could be that Venus has lots of volcanism, and now it's starting to shut down. And so over a very long period of time, it'll eventually lose its whole atmosphere, but at a lower rate because it doesn't spin as fast. So anyway, it's an interesting question.
So just to follow up on that, with the processes you were talking about, the creation of a source of CO2 and creating some sort of atmosphere on Mars, there would be no guarantee that that atmosphere would stay there then, unless the process was continuous, essentially, right?
Yeah, you'd have to make the atmosphere very quickly, and then you would probably lose it pretty slowly on the scale of human lifetimes. And so you just have to play with the rate there, because eventually you would lose it all again.
Right. Thank you very much.
I had a question.
Are
Go
there
ahead.
plans to do research on, so I found it intriguing that the top of Olympus Mons is actually in space. So are there any plans for NASA to do research on what are the effects of having some kind of obviously terrestrial land actually in space?
Yeah, I mean, it's kind of interesting. So, Mars, it's like a fall off of atmosphere, like exponentially as you go up, there's less and less atmosphere. So Olympus Mons is so tall that it's effectively out in space. There's still a little atmosphere around it and everything. But it's kind of interesting because it still has some things about Mars, like dust will be deposited on its summit, but then it shares a lot of similarities with places like the Moon or Mercury, where all of the geology is constantly exposed to space because there is no atmosphere at all. So we definitely study that kind of stuff, micrometeorites and things, space weathering that happens when solar wind hits the surface. And so they would probably be, Olympus Mons would be somewhere between what it's like on the rest of Mars and on what it's like on the Moon.
Thanks.
A question I had about these underground habitations or building like inside these caves. So now on the Earth, if you go deep into the ground or deep into a cave, you get to a typical temperature of about 55 degrees or so. What's that temperature on Mars?
That's a good question. I don't know what it is on Mars. On the Moon, on the Moon it changes with latitude, but it's about it's actually about -15 C. So on Mars, I imagine it would be like, it's basically the annual average temperature. So it's whatever I showed for Spirit during the day, and then during the night, like during the day it was like 70 degrees, and during the night it was -100 or something. So it'd be some kind of near zero temperature.
So still very cold then, not.
Yeah, it'd be cold. The deeper you go down, of course, at some point you're hitting the geothermal gradient, and so near surface caves on Earth, they're the annual average temperature. As you go deeper and deeper, then it gets hotter and hotter, like at the bottom of a really deep mine. So we've never actually measured the geothermal heat flux on Mars. We imagine it to be much, much less than the Earth's, because Mars doesn't have active volcanism. But we have a lander right now on the surface called InSight, which has been measuring, it has a seismometer and measures earthquakes. And I don't know if you've read about it, but it has this probe called the Mole, which is a secondary instrument. And it's supposed to like hammer down into the ground about 15 meters and then take that measurement of how hot it is as you go down. And it just had a lot of technical issues with hammering it in. They hit a rock or something. And so it's taken months, but they're finally got it all the way under the surface now, so they're really hopeful that they might actually be able to do their experiments. So we'll figure out more about that soon. But yeah, it's it depends on latitude, because of course the annual average temperature depends on latitude. If you had a cave somewhere near the equator, it would be a lot nicer down there than near the pole.
Thanks. There are other questions?
Yes, you mentioned that there's no volcanism now. So did the volcanism occur during the heavy bombardment or the late heavy bombardment period, or did it occur from upwelling of the core, let's say the core or the near core of Mars spilling onto the surface?
Yeah, the volcanism on Mars seems to have taken place all the way from the beginning of Martian history that we can see 4.5 billion years ago, all the way up to maybe 2 or 5 million years ago, which in geologic time is like nothing. So we think it's still possible that Mars is volcanologically active, but we've never observed it. And my mission Odyssey has a thermal camera, and we've never seen like a thermal hotspot on Mars or something, but it's possible that we just don't have good enough resolution for that. So when we see a volcano like Olympus Mons, a cool thing to know about it is that if you add up Hawaii, all the Hawaiian Islands, and the underwater seamount chain,
right,
all together, that's about the volume of Olympus Mons. Right. And so Olympus Mons is probably just a plume, like you were talking about, coming up from the core boundary and then feeding this volcano. But since there's no plate tectonics moving the plates over the surface, instead of making a trail of volcanoes, you just make one giant volcano. And so that's probably
hotspot, right?
Yeah, so that's probably happened over the history of Mars.
I see. Thank you.
It was a question.
I have a question. I have a question. Why is the sulfur region so important in terms of the transition?
Well, so what we see about 2006, there was a paper written because the European spacecraft Mars Express went into orbit a couple years before that, and then it took spectra that could let us figure out what minerals were on the surface for the first time. And so we started seeing clay, and we started seeing sulfur minerals, and then we would see like rusty ferrous oxide minerals. And it became clear that all of the clays were really old, from the time period of the river valleys. And all of the sulfur-bearing minerals were from this short time period between 3 billion years and 3.7 billion years. And then all of those ferrous oxides were from 3 billion all the way to the present. And so that made us wonder, what does this sulfur period, this interlude, have to do with the changing habitability of Mars? Like, did you have an enormous volcanic eruption and then the sulfur I wrote a paper about it recently, that sulfur would have cooled the surface dramatically, and then maybe the Martian hydrosphere just never recovered from that event. So people are trying to figure out, why were you making clays, which is what you make when you have lots of water, and then suddenly you're only making sulfates? Does that contain the clue of Mars' habitable demise?
I see. Thank you.
Laura, we lost your mic, but we had your phone, so we still had audio. We just sounded a little teeny there for a sec. I know Dave Mitski posted in the chat, and I'll repeat it. He said, I wonder what the lengthy cloud that has reappeared near a Martian volcano signifies.
Oh, I heard about this cloud. I can't remember what I heard about it, but a lot of times the volcanoes are really tall, and so as the water goes up the volcano, it like warm air can hold water better than cold air. And so even on Earth, as you go up the top of a mountain, then suddenly clouds form at the top of the mountain because the air can't hold the water anymore. And so you're constantly getting clouds at the top of those volcanoes, those 4 volcanoes. That's like a really common place to see Martian clouds.
But it's not indicative of volcanism.
No. I wish it was.
Mm-hmm.
There's another question in the chat. The length of the seasons. Are any seasons longer than others?
Yes, actually. So the way that Mars's orbit is a lot more eccentric than the Earth's. And so it's still like almost a circle, but it's like a couple percent eccentric. And as a result, as you're going through perihelion season, that's when the southern hemisphere, it's southern summer. So the southern summer is relatively hot and relatively short. And then the southern winter is quite long and cool. And the result of that on the surface of Mars is that when it's hot in the southern summer, you get tons of dust devils, and then the dust devils pick up lots of dust, and that's the dust storm season. And if you get the global dust storms and stuff, they're almost invariably, they start in the southern hemisphere during that sort of like hot, short summer. And then, you know, in the northern hemisphere, it's just the opposite. You have like a kind of a longer but cooler summer. And so we have to think about that when we have our solar powered rovers. It introduces a asymmetry in the latitudes where we can send them, because we have to make sure that they'll live through the dust season, and then also that they live through the really cold winter.
Laura, we have another question in the chat. What is your geologist's view of the Martian meteorites? When and where did they come from?
Oh, I don't know. So the meteorites could have only come from, I actually have a meteorite. Where did I put it? I have like a tiny piece of Mars that's like this big from a sugartite. So most of the Martian meteorites, you know, they think there was like the sugartites, the nacolites, and the chassigny, which is just one meteorite, and they seem to be different from each other, but within the sugartites they all seem to be very similar. And so it could be that they're only from a couple impact events, and they all came from the same meteorites and stuff. So as for how old they are, I actually don't know how old they are. Yeah, I haven't studied that.
And then another question, how do you get dust storms if there's no atmosphere?
So there is an atmosphere. It's just, so the Earth's atmosphere is 1 bar, and the Martian atmosphere is 6 millibars. So it's thousands of times less dense, but it's there. So all those sand dunes and stuff, that's from a result of the wind, but the wind's just not very dense. And so a lot of people are wondering, how can you pick up dust? It's kind of hard to pick up dust if you have a very low density atmosphere, but you get these little tornadoes, the dust devils, and they're a lot stronger than regular winds. So they pick up the dust, and then it goes into the clouds, and then it goes all over the place. And a very interesting point of fact is that the Earth's atmosphere has a troposphere, which is warm on the bottom, and then they have an ozone layer, and the ozone layer blocks all the UV rays, and so it gets really hot at the top. And so as a result, we have 2 layers, the troposphere, which is hot on the bottom and cold on the top, and then the stratosphere, which is cold on the bottom and hot on the top. And so anything that's hot on the bottom and cold on the top is unstable, and it's constantly turning over. And that's what causes most of our weather. We live in the troposphere, and then planes fly in the stratosphere because there's not a lot of weather up there. It's totally stratified. It's, you know, hot on top and cold on the bottom. Mars doesn't have oxygen for the most part, so it doesn't have an ozone layer, and as a result it doesn't have a stratosphere, and as a result the troposphere of Mars is extremely tall. And so this mixing that causes all the weather goes almost all the way to the top of the Martian atmosphere. And so that's why little dust storms on the Earth, they stay kind of low, and dust storms on Mars become global.
Anybody else with a question? It's almost dinner time for Laura. She's 3 hours ahead of us, behind us.
It's almost bedtime for you guys.
Yeah, it's getting there,
Not for astronomers, no.
Well, Laura, I want to thank you. It's been a real treat. I know some of the stuff you talked about in Iran, Justin tried to explain to me, but that's a musician trying to explain things to a lawyer and not a geologist. So it was very interesting to hear it from you directly, and great. So glad you could join us on Zoom.
Yeah, so glad to join you guys.
We typically, if there's nothing for the good of the organization, people tend to hang out on Zoom as long as they want to. We typically end the YouTube broadcast, ending the PG section of the program. So Jeremy, I'll wait for you to give the green light on that.
All right, let's stop the live stream. So we're going to end